In this unit, we will see how we can evaluate various conditions on files and also numbers. This is mostly useful when you automate workflows by writing scripts. The UNIX test command allows us to test various file properties and other expressions. This is very useful when we want to write robust shell scripts.
The test program performs a specified test based on its arguments, evaluating them as an expression. It succeeds when the expression is true and fails otherwise. With the -d option, we can test if an argument is a directory. When I run test -d/ and echo directory, the / character denotes the root directory. The test succeeds, and therefore we see as output the word directory. With the -f option, we can test if an argument is a file. Here, the test fails and nothing gets printed. On the other hand, if I run test -f on etc. password, which is a file, the test passes and file is printed. We can also use test to see if two arguments are the same. Running test hi equals there, the program doesn't output anything because the two arguments aren't equal. On the other hand, if I run test hi equals hi and echo same, the program outputs same because the two arguments are now equal. Similarly, we can use test to check if two strings are different. For this purpose, we use bank equals, which is the operator commonly used to check for inequality. Here, hi is different from there, and thus different is printed. We can use test to check if a string is empty, has a length of 0, with a -z option. As an example, I run test -z and equal empty, and we get empty as a result. Equivalently, to check if a string is non-empty, we use the -n option. So, if I run test -n, a string, and echo non-empty, we see that the output is non-empty. When the argument to -z or -n is a variable, it is important to enclose it in double quotes. In this way, when it gets expanded, it will appear as an empty argument in case the variable is empty. Otherwise, there is no argument there, so the program's invocation will probably fail with a usage error. What's more, we can use the -equal option to verify integer equality. For example, here I check if 42 is equal to 32, which obviously evaluates to false. On the other hand, checking whether 42 is equal to 42, we get as a result that the two numbers are equal. There are additional operators we can use. For instance, -lt stands for less than. Here I check if 32 is less than 50, and as expected, we get as output less than because the two numbers are different in this way. With test, we can also examine file properties. For example, whether one file is newer than another. Here, I check if the current directory is newer than the root directory, and we verify that it is. Furthermore, we can test if a directory is writable with a -w option. In this case, we find out that the root directory is indeed writable in this particular system because I run with administrator privileges. Note that Unix systems offer the open square bracket as a synonym for the test command. When we invoke test with this name, we must also terminate the expression with a matching close square bracket. For example, I run the same command as before with as open square bracket -w/ close square bracket. This form is appealing syntactic sugar for expressing arguments to if and while statements. So, instead of writing if test -d/ etc. /bash completion.d to check if the argument is a directory, I can start my command sequence with if open square bracket -d etc. bash completion.d close square bracket. This outputs the number of installed bash completion scripts, which are 5 in this case.
We can evaluate arbitrary numeric and string expressions using the expr command.
In contrast to the test program, expr outputs an expression result on the standard output. Running expr 1 plus 2 naturally results in 3. If I subtract 2 from 10, we get 8. We can also perform multiplications. Here, I multiply 2 by 10, which is equal to 20. Notice the backslash character before the multiplication operator. Because star is interpreted and expanded by the shell as a wildcard, we need to protect it by escaping it with a backslash. We can also calculate the division's remainder with a percent operator. For example, the remainder of 12 divided by 5 is 2. Furthermore, we can compare numbers. Here I check if 10 is less than 50. Again, we need to escape the less than sign with a backslash because it is also used to redirect the standard input. In addition, we can verify integer equality. In this case, 5 equals 12 is false, so we get an equivalent 0 output. We can also perform string comparison. For instance, I check whether John is greater than Mary. The output is 0 because John appears first in dictionary order. Complex expressions follow the typical operator precedence. In this way, 1 plus 20 times 2 performs the multiplication before the addition operation, resulting in 41. To change the typical operator precedence, we enclose an operation we want to prioritize in brackets. Again, brackets have a special meaning to the shell. They invoke a subshell. Therefore, similar to the wildcard, we escape them with a backslash. Another nifty application of the expr command is regular expression matching. In this case, the first argument to expr specifies the lookup string. Here, I enter to be or not to be. Then, the second argument is the matching regular expression, specified after a colon command. Here, I match anything but a space any number of times. We see that there are two characters at the beginning of the specified string occurring without a space. To find the matched part, we enclose the regular expression in brackets. Again, we need to escape them with a backslash. This time, we get as output 2, which corresponds to the string's first word. What's more, we can measure a string's length. For example, to be or not to be is 18 characters long. We can also obtain a string's substring specifying its starting position and length. Here, I start from position 4 and specify that the substring is 2 characters long. This corresponds to the word be. Finally, expr offers a number of short-circuit logical operators. For instance, an empty string or b outputs b because the empty string is interpreted as false. The same applies to 0, which evaluates to false. Therefore, expr 0 or b results in b. Let's now repeat the same expression for the AND operator. So 0 and b. This gives us 0 because 0 is false, so b is never evaluated. Lastly, expr a and b outputs a.
Both text and expr come also as built-in versions in the bash shell. Using them in this way can provide us with a remarkable performance advantage at the expense of limited portability to systems that do not include the bash shell.
Combining expression and test, we can easily write loops. To see an example, I write a loop that initializes a variable I to 0 and tests whether I is less than 10. In case it's not, it outputs the variable's value and then increments it by 1. Executing this loop, we get the numbers from 0 to 9. Bash offers a built-in version of the test and expr commands. Bash's built-in test command is expressed with double square brackets. Similarly, for an expression's evaluation, we use a $sign followed by double brackets. In both cases, we can omit the variable's $sign within the evaluated expression. Let's apply them on the above loop. I restructure it as follows. While square bracket I less than 10 echo $I and then set I to double bracket I plus 1. Obviously, the built-in versions are more efficient because they do not invoke an external test or expr command for each loop iteration. How important is this improvement? Let's find out. I run the first loop for 1000 iterations using the external commands. Thus, I enter time and the loop to time its execution. We see that in this case the loop requires 3 seconds to complete. Repeating the same process using the built-in test and expression commands, we observe that the operation finishes much faster, in less than a second.
This concludes our unit on processing data through testing and expressions. Stay with us.